Hey, good morning, everybody. Hope you guys are doing well. Checking out today's agenda. We're gonna do a quick lesson on craters and momentum. Then we're gonna go over yesterday's stuff on the crash barrier. Heard there was a little confusion, so we're gonna try to get some of that answered. I'm also gonna post a bunch of answer keys today, so you can spend some time checking work on the practice quiz, as well as all the homework assignments I still need to go make a key for. I'll be doing that. And last up, hopefully with all your questions answered on the crash barrier, you guys can get that going again and try to make some progress. I figure instead of a 2-day with me being out, it'll probably be a 3-day lab. So we'll try to get some questions answered Monday as well. That'll push back the quiz to Monday, and that might push back the tests as far as maybe Wednesday or Thursday, so we'll see. All right, so getting started. We're gonna cover impulse craters and weathering. Pretty short, pretty straightforward topic. Let's get going. So you guys are going to know when cratering occurs, how meteors are different, and how momentum is involved in the process. We're also going to make sure that we understand this is mostly an inelastic collision. Now, in real life, is anything either 100% elastic or 100% inelastic? No, it's somewhere in between. By assuming it's one or the other, we're kind of making a simplification to make the problem-solving process easier. We're going to look at how it is and isn't elastic. It's mostly inelastic. And last up, of course, the reason we don't have a ton of meteor craters is weathering. So we're going to make sure we understand, like, how do these meteor craters get erased? That's definitely true on Earth. It's not necessarily as true on other planets, and we're going to look at the differences there. So, first thing you need to know, our solar system is about 4.6 billion years old. And basically, solar systems start out as a nebula, which is just a big giant gas cloud. So if you have a big giant gas cloud, it may or may not have any noticeable rotation when it's out here. But as things start to collapse and pull inward, have you guys ever done the thing where your arms are out and you're spinning and you pull your arms in and it'll end up spinning a lot faster? That is actually also a conservation of momentum principle. The thing is, it's rotational momentum and not linear momentum. So instead of momentum in a straight line, it's momentum of a rotating system. So point is, as gravity starts to pull in this gas cloud, any tiny net difference in velocity one direction or the other, clockwise or counterclockwise, is going to get accentuated. And it may have started out completely random, but just the tiniest difference one way or the other, when you pull that in over, dozens or even hundreds of AU, astronomical units, that rotation starts to become more and more noticeable, whatever random starting point ahead. In addition, instead of just a big kind of 3D cloud, through collisions and gravity, it'll tend to form an accretion disk. So you can see kind of an artistic rendering of a very early solar system here. It has flattened out into a disk, and more stuff just tends to be rotating one way than the other way. There's always some randomness to how that gets started, but that randomness becomes accentuated later on until you have kind of a dominant mode of rotation for the entire system. Now, 4.6 billion years, that's a long time for our solar system to have been around. And early in the process, it was more like fuzzy with small junk everywhere. It takes quite a while for gravity to clump things up and start to form planets. Once you do start to get some major chunks though, those chunks, each time they're able to revolve around the sun, they will sweep the path in front of them. So this is a great illustration. I like this one because it has the idea that this planet, every time it goes around, is sweeping out that space. Now obviously this is not drawn to scale, an artistic rendering, but it makes a point. The planet is going to basically clear out all the junk within its orbital path, either by gravity or direct impacts. And so that means that early on, 4.6 billion to 4.0 billion years ago, we had a ton of meteorite impacts on the early planets. They were getting pummeled all the time. Only by about 2.5 billion years ago was all the junk swept out. And now meteorite impacts are much less common, although they do happen from time to time still. There's still some random stuff here. So, idea number one, solar system is very old. Rotational momentum is conserved. And so even with a random start out here, as things collapse, you'll tend to get more noticeable rotation when it's inside. As planets start to form through clumping by gravity, it will sweep out the space in front of them and receive a whole lot of impacts early on in their formation. Those impacts start to dwindle over time. With less junk lying out there, there's fewer things to run into. Now, what's the difference between a meteor and a meteorite and a meteoroid? And so, let's see, the meteorite is the one that's actually going to impact Earth, whereas a meteor is one that's going to burn up in the atmosphere. And a meteoroid is one that is present in outer space but hasn't yet interacted with Earth or some other planet. Okay, so look at the diagram. Which one made it to the ground? The meteorites. The meteor, that one is going to burn up in the atmosphere. First thing to know about that is a lot of people think that skin drag, which is friction across the edges of it, is the thing causing it to get hot. And that's generally not the big idea. Like, it contributes a small amount. The big idea is that when you compress air really quickly, that air heats up. So air compression, it's called adiabatic heating. That's going to be the thing that actually heats up the meteor. So yeah, a lot of them burn up in the atmosphere and never make it down to the ground. Speeds on these things tend to be really, really, really fast. We're looking at 25,000 miles per hour up to 160,000 miles per hour. That is like orders of magnitude faster than what we think of fast. So even a very small meteor or meteorite tends to be able to hit the ground and annihilate things and or push its way through the atmosphere and burn itself up. So a couple of things to think about there is the speeds these things are going, whether or not they make it to the ground or not. Now, if they do make it to the ground, you don't think of rock as a flexible, like bouncy, elastic material, right? But with the speeds and momentums they're going, it'll actually compress rock and put a shockwave through the ground. Because we're doing work on something, we're providing a ton of energy in kind of a chaotic way. That translates to heating, and so to actually melt the surface layer of whatever it impacts. And what you can see in this kind of step-by-step process is mostly the projectile, the meteorite, is going to get buried and mixed with this rock here and kind of melted into the top layer. And we're actually going to see some rebound on the Earth, and it'll kind of make a bulge in the center back the other direction. There is some stuff that gets kicked out, and that's called ejecta. So yeah, there is going to be some elasticity to this. It's not fully inelastic like I mentioned earlier. Check out a quick demo here. This is the awesome teacher education version. You can see ejecta coming out pretty symmetrically. And if we look inside that hole, we should see a little bit of that bounce back in the center. That'll be most true at extremely high speeds. Now what's really cool is, can you get the impact crater to be asymmetrical? Can you get it to be lopsided by having this thing come in at an angle? Obviously, if it comes down straight down, it's going to make a nice circle. What's weird is, this is a computer simulation of increasing the degrees of impact, and these are at different times. You can see straight down, perfect circle. Lopsided, the crater itself is still pretty circular. The ejecta is not. Would you guys say that is or isn't a conservation of momentum? Meteor was coming in this way, and the ejecta ends up going the same way, kind of. So hopefully you're thinking, oh yeah, that makes sense. A lot of the ejecta is going to go the direction that the meteorite was heading. It's going to bounce it right out the side. What's weird though is just the way the shockwave forms and the way things rebound and bounce out and eject. The craters tend to stay pretty circular. So it takes a really, really, really glancing strike, almost kind of parallel to the surface, to be able to get these oblong craters like this. So it's pretty rare to get a weird shaped crater. Even at fairly steep angles, it still looks pretty circular. Just difference is which direction does the dust get kicked. All right, there's Meteor Crater in Arizona. If you haven't been, it's pretty cool. It's kind of over by Winslow. You're driving through that highway, might as well stop in and check it out if you ever get a chance. That's, I think, one of the biggest ones in the US that's still around. Okay, now, question for you. When we look around the Earth, do we see a ton of meteors? Like, is the Earth basically blanketed in them? The answer is no. Meteor craters on Earth are relatively rare. So the question is that because Earth did not get hit by meteorites back in the early formation of the solar system? No, of course we did. There's nothing special about Earth in that sense. So what's happening is, on Earth, they're getting erased over time. We have a couple things going on. We have active molten core, we have tectonic activity, and we have an atmosphere, especially including rain. So we're going to get really fast weathering compared to other planets with no atmosphere or no rain. Stuff's going to get eroded or blown away, basically. We're also going to get volcano eruptions, tectonic plate subduction, and other stuff kind of erasing surface features over time. That's why Earth is relatively smoothed out compared to some of the other places that don't have that. If they don't have an atmosphere, and they don't have kind of active volcanic and tectonic activity, then you are going to see basically all of the original craters, unless there's literally like craters on top of craters on top of craters, in which case you're just seeing the newest ones. So if you look at basically a whole bunch of other surfaces, you can see, yep, there's not a whole lot of erosion going on there. And no real atmosphere or volcanic activity to erase stuff. That's just important to think about. All the planets got bombarded by stuff. The ones on Earth have generally been erased through erosion, weathering, and tectonic and volcanic. And a little more about that. It's been a very, very long time since these original impacts. So there's been a long time for those forces to be able to erase them. One thing to think about too is that when I say weathering due to water, I'm actually thinking not just like rubbing against it, grinding it away, water, water carrying like sand in it, kind of eating away at stuff, the way we would for wind weathering. I'm also thinking of water-based weathering being a chemical process. It's able to dissolve sediment in the rock, some minerals, and erode the rock that way. So water also provides chemical erosion, not just physical erosion. And quick questions for you. Bigger craters come from more or less momentum on the impact? Hopefully, obvious answer is yeah, more momentum should leave a bigger crater. Does the rock have to be very big if it's going, what did we say, 25,000 to 160,000 miles per hour? No, it can be a fairly small rock. So that's kind of terrifying. If you guys have heard of one of the meteorite strikes over Russia, I think it was maybe 5-6 years back, very small rock, exploded midair, didn't even quite make it to ground, but the shockwave from the midair explosion knocked out windows, kind of deafened people for miles. There's some cool footage of it on YouTube. Dramatic event to experience. And that's about it for that. Let me get you guys one other one. That was a quick wrap up of our meteor one. Let's start going over the lab thing here. Just a sec. Reset this. Come on. Not really the vibe I was going for with music here, whatever. Okay, crash barrier. So this is stuff we covered yesterday, hopefully, maybe. It happened. Your goal is to be able to make and interpret some force time graphs to understand how well your crash barrier is working. The smart carts are going to generate that. Configuring the smart carts does take a couple steps. And what we need to do is start out by getting a baseline set of readings with no barrier in place where they just smack directly into the wall. Then when you put your barrier in place, to be able to gently and softly catch the cart over a long time, providing a low force, then you should have something that's considered successful. We're trying to make this a compact device and yet still manage the forces involved in the momentum transfer efficiently. That's kind of a tricky goal to get going there. All right, now we got to interpret and look through these graphs here. So question for you first is, how many seconds across is that event? And I don't want anybody saying 4. Okay, this is not the time that's important. This is just how long did it take for them to hit the stopwatch and then have the crash happen. That's not the thing we want to pay attention to. What you want to pay attention to is the difference between the start and end of the crash. Okay, so the change in time was from 4 to 7. Okay, so that's a 3-second wide event. And it's a 2 Newton tall event. Okay, so I'm looking at the area of this on a force time graph. The area of this, force times time, is impulse. So I can basically, oh yeah, width is 3, height is 2, impulse is 6. Okay, so that's really cool. On these force graphs, you can basically identify the impulse over time immediately. So let's see what we got here. We've got a impulse of 6. And I also said we have a mass of 2, and we're supposed to find the change in velocity. Okay, one of my equations is that impulse is mass times change in velocity. Another one, of course, is impulse is force times time. What we're really doing is we're using this one first, and then assigning that value here. You could even write this like this if you wanted to. Yep, anyway, 6 equals 2 times delta V. Cool. Change in velocity is 3 meters per second. There's an example of that first problem all thought out. Let's jump back. Okay. Now we've got a 2-stage event, like the dreaded level on the simulator you guys were doing on Monday. It's 2 impulses combined causing some difference. Let's see, one of these is the time on this one too. The answer is no. Sorry, I got attacked by my cat. She likes jumping through the green screen. Okay. We got 2. No, that's not a time of 2, right? That's a difference of 2 to 7. That's a 5-second wide event. and it's a too tall event, which means that my impulse on that one is plus 10. Okay, so I'm looking at the width of the blue square and the height of the blue square. The multiple is the impulse. Over here, we've got a width of 2, and let's see, we got a height of -4, and so that impulse is -8. And so I'm just looking at, okay, those things combined, if this thing was at rest, it started with the impulse of 0. And so I'm just saying, okay, started with the impulse, oops, sorry, wrong one. Started with the impulse of 0, we gained 10 from the box that was 5 by 2. We lost 8 from the box that was 2 times -4. And so now my combined impulse is +2 Newton seconds or kilogram meters per second. So we can think about those events that way too. We can have more than one thing happen at once. All right, now here's an important question for you, and this one's going to look kind of like what you're doing in the lab. One of these two events is a high force over a short period of time. That's bad, and that's what your baseline should look like. You guys should be getting a very narrow, very tall spike, and it should be close to 100 newtons if you've set up everything in your lab results right. That's the crash with no barrier, the red one. With the barrier, what we're going to do is we're going to elongate the time of impact, and in the process we can use a much, much lower force, which will mean it'll be safer for the people in the car. Okay, so the blue one is a safe impact, the red one is a dangerous impact. Our crash barrier is supposed to basically take a shape like this and do that to it. That's how you know you're getting better. Which one changes the speed more? This one is a 6 times 2. This one is a 2 times 6. The answer is, in both cases, these had the same impulse. They might have both stopped the same car. It's not that one of them changed the velocity of the car more than the other. It's the same change. It's just happening differently. Like you could catch a water balloon or you could catch a water balloon. There's two different ways to do that. In both cases, we're stopping the water balloon. It's not that the total momentum changed more or less. It's just we're manipulating force and time to be able to get the multiple that we want out of that. Now, one problem is realistic data isn't these nice rectangles. Realistic data is going to be a lot more like a triangular spike. So I've got a quick question for you. Let's say I had a box, and the box is a 2 by 2. What's the area of that box? Oh yeah, it's base times height, so area is 4, right? If I have a triangle, whether it's that kind of a triangle or this kind of a triangle, it really doesn't matter. That is now half of the box, right? So keep in mind the area of a triangle is 1/2 base times height. All right, 1/2 base times height. So then we jump back over. Let's see, this red one is 1 wide and 10 tall. And so if this were a rectangle, I'd say the impulse of the red one is 10, but because it's a triangle, it's half that. So impulse of the red one is 5. Meanwhile, this blue one is 2 wide, and it is -7. So if that were a rectangle, I'd say this thing is a -14. But since that's a triangle, it's only a -7. Okay, so when working with a realistic, kind of more triangular spike than a nice pretty rectangle, make sure you're using half the area of those shapes. All right, now let's talk about some other issues. The events that we're trying to measure are happening over extremely short periods of time. This makes this tricky. So what a sampling rate is how often the sensor is checking for a value. This is a setting that we're going to have to go change on the smart cards. And it's going to be measured in hertz. A hertz is a cycle per second. So what we're looking at is, oops, sorry. If we're looking at, like we're only checking infrequently, nothing happens, nothing happens, nothing happens. And we get these dots that are pretty widely spaced out, you're going to assume, okay, the collision started here, the collision ended here, and that's 1, 2, 3, 4, 5 dots. Let's say that each dot is 0.2 seconds. So that our sampling rate, how often we check for a measurement. Sampling rate is every 0.2 seconds. If that were the case, cool, I've got my time value. That's not a big problem. What about the force value? Let's say we check the graph and this thing is 60 newtons. Here's the problem. Problem is, if we're not checking very often, the real shape could have been this. Did we get the correct height on what really happened? No. we're definitely underestimating. We've got a systematic error where we're not catching the peak of the collision. And by not getting that piece of data, we're going to be way off in whatever happens. Maybe the real peak is way, way up there at like 180 newtons, which by the way, hopefully it's not that high because the carts have a 100 Newton limit on what the sensor can handle. That's why we're calibrating for that to be the biggest possible. Don't go over 100. It's going to be wrong data and it could damage the cart. Okay, so what we need to do to fix this problem is we just need to take dots a lot more often. If our cart is sampling much more often, we will definitely have a higher probability of actually getting the correct value. Like, see how more dots equals better data when events are this brief? What you guys need to do is set your sampling rate to 1000 hertz. A hertz is a unit label we'll talk about more in waves, and what it means is a cycle per second. So it's basically cycling 1000 times per second. That means that each dot is worth 0.001 seconds. Okay, each dot is worth 1,000th of a second. And so when you look at these graphs, you guys know when you got a graph going, there's a resize button, right? So you always resize your graphs so you can see what's going on. And I would go in and you can actually click on a dot and you can get it to display the value. And I would click on the first dot and I'd click on the second dot. And let's say this one is 4.312 and this is 4.31. Let's see, 4.323. What time do you write down for the time of impact? You write down the starting time or the ending time? No, don't do either of those. We don't care that the cart took 4 seconds to get down the track. That's not what's important. We're trying to measure how long the collision takes place over. What we're going to do is we're going to subtract these two numbers. And so you can either pull the data right out of the software by clicking on and showing values for stuff, or the other thing you could do is you could just count dots. Remember that each dot is worth 0.001 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 11. Okay, it must be 11 of those. That's how long my collision took place over. Or you could get the same answer by subtracting these two. Like that minus that is going to be the same answer. So that's an option for how to get the time of impact. Obviously, the other thing you're looking for is what is the force value in newtons at the peak of the collision. By doing those two things, you can basically check how much impulse you're providing. And we are trying to get that tall, steep spike on the baseline to flatten out to a shallow, wide spike on our really good crash barriers. All right. So there we go. A couple different ideas there. In this, there's a very detailed configuration guide. Keep in mind that 1,000 samples per second is a lot for both the cart and your Chromebook to handle. So 1 kilohertz should be the force sensor sample rate only. If you set all your sensors to sample that fast, you're going to crash your Chromebook with the data overload. Things are going to get buggy. So when you're setting this up, make sure you're checking periodically at 1 kilohertz, 1,000 cycles per second. That'll get you the time resolution you need to measure these things accurately. This setting's kind of one we haven't messed with here, but there's all real clear instructions, so just make sure you follow the instructions in detail. Okay, let's talk about setup here. Not sure how far we got with this yesterday. First step, let's see, here's my desk. Here's the 2 doors. You guys are welcome to, here's the countertops. You guys are welcome to move the tables around the outside, as long as you put them back when you're done, to be like that. Okay, that way you can take a cart and a track. By the way, the tracks are located back here. You can carefully grab a track, and you can jam it against the wall. Make sure that's a nice right angle, and make sure that it's pushed up against the wall. We want that cart to go right into the wall. And get a textbook underneath this thing somewhere so that it's tilted. And that way we're going to just run the cart down the track. You just basically let it go from 100 centimeters before the wall. It's supposed to have a 100 centimeter run up where it hits the wall. And yeah, there's a ruler right on the tracks, a little yellow ruler. So you can basically let it go with the front of the car at 100. Make sure that the bumper end is facing the wall because that's where the force sensor is. And we want to just have like 1 or 2 textbooks under the track that when it hits the wall, the peak force value is just barely less than 100 newtons. That's what you want to be doing on your baseline. Run it a bunch of times, do multiple trials, and average those force values together. And from that point forward, as long as your average is a little bit under 100 newtons, like I'd say anything over 80, anything less than 100, those are all fine setups. That means your system's configured and you're ready to go. Then what you're going to do is, let's get a side view of the track here. Here's the track, here's the textbook, here's the wall, here's 100, here's 0. What you're going to do is put a barrier, and it's nice and jammed into the wall, like nice and firm, right? What you're going to do is put some kind of a barrier right here. I don't know what it's going to be. You guys are in charge of that. And let's say the front of this barrier is at 5. That means that's the width of your barrier. By the way, the minimum allowed is 2. But we are shooting for compact, so I'd consider making a relatively compact barrier that's right at 2 centimeters or just above 2 centimeters. It can be taped to the wall or something if you needed to. What I'm going to do is, if this front of this barrier is at 5, I'm going to start running my cart from 105. We want the run up to be 100 centimeters before it hits anything. And you guys need to be recording the width of this and doing multiple trials and recording the force values associated with that. And I would also describe what the barrier is. So let's see, what could a data table look like? If I was in Microsoft Excel or Google Sheets, I would say I would have a description, a width in centimeters, and then I'd have force data. Newtons, trial 1, trial 2, trial 3, do a bunch of trials, and eventually you're going to average, get your precision, etc. Like let's say the first barrier is a cardboard accordion that was 5 centimeters wide. And my values were 30, 32, 31. Oh, you know, another thing we're gonna need is we're gonna need the time of impact. I would just maybe record that once. I don't think I'd get all the trials on that. But let's say time of impact is 0.07 seconds now, using the method I showed you guys earlier. That's probably the kind of stuff that goes in your data table. In the long run, what you're going to do is get the goodness factor going. And the way that works is it's the force of your control group, which that's the number, remember, that's the number that without the barrier, it should have been close to 100. And you're going to divide it by the force with the barrier, that's your experimental group, and also by the length in centimeters. So let's say I had this configured to be 90. I was getting pretty close to 100 newtons without the barrier. With the barrier, it looks like my average is going to be 31, and my length is 5. And so what I'm trying to do is get that ratio to be as high of a number as possible. This is actually not looking so good so far. This is apparently a pretty bad barrier. Yeah, there we go. And that number is not even 1 yet. This is your goodness factor or your Q factor. The way the lab gets scored is to try to get this number as big as possible. The record for Oakmont is 22. I think that you guys have to be over 2 to get full credit. Should be pretty easy to get over 2. A lot of groups I had last year running kind of in the 10s to 20s. So hopefully you guys can find a barrier that's just gently over a long period of time and nice and evenly slowing the cart down, but isn't necessarily stopping it all at once over a short period of time. That's bad. Make sure too that your barrier is pushing on the bumper. It doesn't count to push around the bumper and bypass the force sensor. We'll kind of check for that stuff on Monday when you guys think you have good ones you want to get recorded. All right, so that was it. Use the bumper end. Make sure you got the sample rate and understand how to record time. Get your control group as high as you can, but under 100 newtons. Watch out on crashing your Chromebooks. This amount of data can do that. They're not that powerful. And then also how to calculate your score. You can program that right into your spreadsheet, by the way. Remember to start with the equal sign, click on the cell you want on the numerator, hit the divide key, click on the 2 things you want in the denominator. And so you should be able to calculate that out dynamically and then fill down and have your spreadsheet do all this math for you. All right, hopefully that helped and got you guys back on track. I hope to be back in person with you guys on Monday. and I'll get a bunch of answer keys uploaded later and in time for class, so you guys can continue checking work on that stuff. All right, have a good one, everybody. Bye.